really appreciate the opportunity to be here and talk about transformer testing. It's one of my favorite topics to talk about. Just a little background again about myself is I started my career at Doble Engineering in the field, testing transformers with Doble and performing training and analysis of test results. And then I moved to Omicron as well, about 6 years later after that, and worked in again the what's called the primary side of things, which is transformers, breakers, CTs, PTs, ground grid testing, and then moved into sales. And the last 5 years that I was with Omicron for about 15 years. I was the national sales manager there. And then I recently moved to intellirent to help support training and sharing knowledge for customers and testers. So, transformer testing is really an exciting topic, and it has evolved just like Randolph has talked about with the different test techniques that we have and the tools that you have to try to find the problems before they become a big problem, and that's our goal here today. So. My focus for this presentation is to kind of give an overview of the different test techniques and some modern techniques to try to help you in the field learn about transformer testing and interpretate results of the different tests. So the presentation will be broken up into two parts. We will first dive into the fundamentals and failure mechanisms. So, a little overview of transformer failures, the components of transformers, what is power factor testing, exciting current TTR, winding resistance. We'll go through a case study there. Then we get into leakage reactants and something called FRSL, frequency response of stray losses. And then we move into some advanced testing, which I don't think they're advanced, but they're more modern, newer testing that definitely should you should know about and have in your toolkit when you need them, called sweep frequency response analysis (SFRA) and dielectric frequency response (DFR). And then we'll wrap it up with another case study that kind of combines multiple tests to kind of see how they all interact to pinpoint a problem. So, with transformer failures in general, the top three bulk transformer, majority of transformers kind of fall into these three categories. You have dielectric. So when I think of dielectric, I think of insulation. I think of PD. I think of breakdowns within the insulation that track to ground and they fail. So I could think of like inside the transformer, the overall transformer insulation. I could think of bushing failures, which happen a lot. Mechanical failures is the second major one. So movements. Whenever there's like a fault that happens, like a through fault in a transformer, the forces that occur inside the transformer that push the windings apart, it's really amazing, and that's where you see a lot of these transformer failures happen, or if there's core or structural type of looseness or damage that occurs. And then the third one is electrical. So if you have an open circuit or your connections degrade, LTCs, kind of like the clamping of things and the pressure on those connections. So electrical failures as well. So in our toolkit, to try to help you, it's really evolved over time, and the first line of defense always is called DGA, your dissolved gas analysis, and that's what you're trying to take a oil sample and look at gas and patterns and try to figure out what's happening in your transformer. It's a great tool to have, and provides a lot of valuable information. Then you have power factor and capacitance. This is an overall power factor, your health of your insulation system, um, that we'll get into. You have TTR, or your transformer turns ratio, that looks at the ratio of the transformer. DC winding resistance. So this is a great test to look at any types of loose connections or like LTC, DETC type connection points where you want to see how good and solid that connection.
or if like the bushing is connected to the high voltage or low voltage winding. How tight is that connection? Has it loosened up? DFR, dielectric frequency response, that's looking at moisture in the paper. It's a direct measurement that really zones in on the moisture. Insulation resistance, again, another type of overall insulation test. Oil screening, testing exciting current, which looks at the magnetic circuit of the transformer. Leakage reactance testing, that looks at the leakage channel and winding deformation in the transformer. SFRA, which is one of my favorites, mechanical integrity. Anything that moves in a transformer, SFRA picks it up. Um, Thermal imaging, um, really popular these days, and now the thermal imaging cameras can even find PD, and it's really exciting to see that evolve over time. And partial discharge is becoming more and more popular for online PD and doing it as well. So a really big toolkit that everybody has. And these are the tests that I'm going to focus on today for transformer testing is power factor, TTR, DC winding resistance, DFR, exciting current, leakage reactance, and SFRA. But before we can even get into that, we just got to like talk a little bit about the components of the transformer, just a basic overview of the transformer. So when you walk up to a transformer and you want to do testing on this transformer, you need to walk around and make sure the transformer is solidly grounded and has good grounds to the transformer tank, because also your test set has to have a good solid ground to get good results for it. Then you identify your DETC, what position it's in. Does it have a LTC? Is it nitrogen blanketed or is it a free breather? The bushings, is it a delta? Is it a Y? Where are my bushings located and things like that. So you can see in the picture, um, there's a lot. Does it have a shield, for example, between the high voltage and low voltage one? And that will change your test plan and procedures for testing the transformer for sure. But understanding the transformer and the different components are very important to these different tests and the procedures. And going into the tests, I'm going to kickstart everything with power factor. So power factor is a really great tool to identify the overall health of the insulation. So what you do is you short all the high side together and then the low side together. And what that does is that breaks up a transformer insulation system into these three components. It's called CH, CHL, and CL. Because one thing about power factor is it's a sensitive test, but it's more sensitive if you can break it up into smaller insulation systems. And that I wish we could take one short and short all the bushings, do one test, but that wouldn't tell us, if we had a little problem on the high side, it wouldn't be sensitive enough to be able to identify a power factor. So that's why we have to break this up like this. So we would do a test. We put our high voltage lead on the high side and our low voltage lead on the low side. Notice the transformer tank is grounded, and we're going to do a test that measures CHL, and you do a test that measures CH. And then we flip the leads and we run another test from the low side, and we're going to measure CL and CHL. Here's an example of the test results of CH, CHL, and CL. And notice there's a couple key things that a typical power factor measurement will have. One thing that's called capacitance, and a capacitance is the physical attributes in that insulation system. So if anything changes, if oil comes out of the bushing or the transformer, that capacitance would change. Um, the watts loss, that's the real power that's getting through the insulation system, and we want that to be really low, which is directly related to the power factor as well. So power factor is actually calculated, it's not directly measured.
And your power factor, instead of having like a generator that you want to generate power and send it to the customer and having it basically a 1% or 100% real power, for insulation, we want to stop all the real power and have it very, very low. So a perfect power factor would be about zero point 0.2 to maybe zero point 0.3 in that range, a brand new transformer. Um, and be able to trend it over time. And this is all done at 60 hertz power factor. So you can see all these power factors are 0.28, 0.21, really, really good condition, low watts, and healthy insulation system. And finally, you see the mode. You have GST, GST Guard A, UST. That's the test mode, which I mentioned of the different insulations. Well, your test set will actually do the switching for you. So it switches between these test modes to measure the specific insulation system, so you don't have to do that anymore. When it comes to bushings with higher voltage bushing class, they'll have these taps, a test tap and a potential tap. And we break that bushing insulation into two parts. You have what's called C1, that's your main insulation from the center tap to the test tap. And you're basically, it's paper foil, paper foil, paper foil. We want to measure that. That's the critical part of it. And then the C2, which is basically from that test tap to ground, which is mainly that oil. We want to measure that too, because that can give us an indication is any air and moisture getting inside the oil, which then will get inside the main insulation. C2 can be a little more challenging to test because um, that tap, once you undo it, you could get moisture inside of it, which affects the result. And then when you connect into that tap, you have to make sure you float your test lead, your injection, and make sure that's not touching ground, or that couples into the measurement as well. So, C1 test, basically you connect to the high side and you measure to the tap, and it's a UST. And we're going to measure each tap in each C1. And it's really important that you only remove that one tap at a time. Every other tap should be grounded. Um, so you remove it, hook it up, test, connect it back in, and then move to the next one. Here's an example of the C1 test. And what's nice about C1 is that typically it has a nameplate for each bushing. And so you want to match what the factory did that's stamped on that nameplate for power factor and for capacitance. Now, in modern test sets, there's something called extended power factor. Each manufacturer has a different kind of mode that they call it. But basically, what it is it's varying the frequency outside of the 60 hertz, and it's really, really good for bushings and overall insulation. I'll get to that, but for bushings, you can really identify the moisture that's happening in that main insulation system. So if you look at the two bottom pictures, this is a C1 test, and this is again just power factor. It's the same connections, but that low frequencies in that two pictures on the bottom, it kicks up. And if it kicks up below 60 hertz, it really indicates an insulation, a moisture content issue. And that curve going through 60, that slope is not the slope we're looking for. We're looking for a downhill slope like that. So if you see the top right, all three bushings, H1, C1s, are nice going through down, and the bottom two out of the three bushings have that nice slope that we're looking for. And then there's one that would definitely be rated for investigate and closely monitored as well. So that extended power factor kind of like helps flag some of those early indications of bushing moisture issues. A C2 test is where we energize at the tap and you measure at the uh, um, you energize at the tap and you measure to ground. One big thing is this is at a much lower voltage test point. Instead of let's say 10 kV, we're only doing at 500 volts. And again, we want to compare the capacitance of each and the power factor of each bushing. For exciting current, this is a test. It's an open circuit test, and we're going to apply a voltage to, let's say, the A phase, and we're going to see how much current does it take to create that transformer action in that core. So we're going to do it for each phase, the A phase, the B phase, and the C phase. And we're going to take the recording of the voltage, what voltage, we're going to inject a voltage and what current it took for each phase. And this is a really nice test to look at any short circuit turns, any open turns in the transformer, core problems, so core constructions, laminations, gaps, shorted laminations, saturated core. So this is a test that is affected by any DC magnetism. So you want to make sure you do this test before any DC test that you do. But I can tell you that if you perform this test and you do have some type of core or shorted turn, your test set will bark at you and it will be really tough for you to perform this measurement. So if what you're really looking for, I put up here the most common pattern for a high-low-high pattern, which is the A phase is the green, is a high. The B phase is in the middle of that three-phase transformer, and the C phase is on the outside. So the A and the C, the two outside phases, should be very close to each other for current, and the B phase, due to where it is, and when you run this test, should be lower. And you're looking for this high-low-high pattern. There's other patterns, but I just put the most popular one. And if the A and the C are outside of that, the next phase would be is to demag the transformer and to repeat the test. And a lot of winding resistance test sets now can easily demag transformers to help it out. TTR, where we inject a voltage on the high side of the transformer and you measure the voltage on the low side of the transformer. We're going to do that for A, B, and C phase, and also for the different taps. And speaking of taps, there's what's called a de-energized taps and a LTC. So de-energized means you cannot move that tap changer unless if it's de-energized. And you have to really be careful because a lot of customers or a lot of utilities do not want to ever move that de-energized tap changer. Typically there's a lock on it and it stays in that place where you put it there. The LTC load tap changer is the one where it moves as it's online, and we need to test every tap for that for sure. And IEEE will have it for a 0.5% tolerance between nameplate and your results. And what you really do is compare it to nameplate, of course, but I'm looking at a lot of these results face-to-face comparison and phase angle analysis. So it's really good if you have the ability to graph these things and kind of see this. Winding resistance. So moving on to winding resistance, this is what's called a DC test. And I have up here a transformer equivalent circuit. So this is one phase of the transformer equivalent circuit. So on the left side where R1 and L1, that would be the high voltage side. LMRN is the core. And then the secondary side is L2R2 side of it. So that would be the low voltage side. So if I apply a DC current into the high side, basically with time and that current, that L1 and LM would short out and I would be just left with that R, the resistance of that high side. So I take my measurement, I inject, let's say 5 amps or 10 amps into the A phase of the high side, and over time the test set will take a measurement once it's stable where the R maintains its stability, and we're going to just measure that R, and that R should be similar for each phase. And this is where I really like wine and resistance a lot because it really identifies a lot of problems with connections. So any or a short circuit turn, open turns, defective tap changers. So like if a tap changer, the pressure on that tap changer, any of that changes over time, loose connections. So as I mentioned, that bushing coming down, I was involved in a case study where we were able to find where it wasn't tightened compared to the other A, B, and C phases um, as well. So the only negative side of this is a DC test. So you got to magnetize that transformer. So you got to make sure you know when to perform this, and it's typically done at the end. And you want to make sure you demag after you perform this test. What you do is you compare if you have factory results, previous results, and then phase to phase as well. Um, DC wine resistance. This is a case that I was involved in, just to share an example. So here's a result of an LTC. So we did a wine resistance on all taps. So we started from the low side, went to the high side, then we went back to the low side. So back through from the different high to low, I meant low to high, and then high to low. And you can see 14R and 4L had high wine resistance results. And you're like, oh, okay. Because the DGA from the LTC also showed there was some gas and some heat going on. So when we looked at the nameplate, now I got to figure out where 14R and 4L are. And we look at the nameplate, we see that they're on this lead 7. So 14R is 7 and 7, and 4L happen to be on 7 and 7. So when I look at when then they took out all the oil out of the LTC and they did a internal investigation, and when what they found is you can see on that lead 7, you can see the burn-in, the coking of that connector. You can also see the insulation around it that kind of, it was so brittle. There was all pieces actually in that LTC compartment in there too. So they were able to replace that lead and re-energize that transformer. So now I want to move on to mechanical health. So we looked at like connections, we looked at insulation, we looked at the magnetic circuit. But now let's look at mechanical health of a transformer and the two big tests to see if something moved in a transformer. You still have capacitance, don't get me wrong, but leakage reactance and SFRA. So leakage reactance is a really, really good test to try to find if a wind-in has shifted inside or out, like a through fault, something pushed that wind-in out. And leakage reactance, it's called a short circuit test. So what we want to do, unlike an open circuit test, a short circuit is where we short the low side of a transformer. And what that does is, because in this circuit here that I showed previously, but that core is such a high impedance. So when I inject on the high side and I short the low side, the current always flows through the path of least resistance. So it goes around the core, right back into my test set. And we're gonna take measurements by shorting the low side, inject on the high side, and we're gonna measure the impedance of each phase. So you have something called a three-phase equivalent, which you're gonna match the nameplate. So what's nice about this is that the factory um, does this at the factory and they stamp it on the nameplate. So we have one data point to try to compare to. And then we also do, which I like even better, a per phase. So I don't care what tap changer position is on, because the three-phase equivalent, you have to do it exactly what position in the factory, which is typically nominal. And then the per phase, you just got to make sure the taps are in the same position that you do put it on. So in the per phase, you're going to compare among each other to look at the leakage channel, which is a small little gap between the high voltage winding and the low voltage winding in the transformer. So here's a picture of a nameplate just to show you this is a delta Y. And in this nameplate, the impedance was 6.85%. So again, the three-phase equivalent, I would measure, I'd do 3 tests. I'd be short on the low side. And then I would, the software will calculate the three-phase equivalent, which would try to match at 6.85. And then the per phase, I would do each phase independently. So I do A phase and just short A phase, B phase, just short B phase, C phase, just short C phase. Again, what's nice is with a modern test set, things have evolved, leakage reactance. Now there's something called FRSL. So FRSL is called frequency response stray losses. So now we can get it down to strand shorts. So the goal of this result is during the leakage reactance test to just hit the checkbox button if the test set can do it and be able to measure a strand to strand short. So if you have if your DGA shows a little overheating and paper burning, this is the test I would like to pull out and go out there and run. And basically, if you look at those, the picture on the left, see how it's wound? One turn is a bunch of those center conductors. And if one of those strand to strands gets shorted, that insulation breakdown, that's what we're trying to pick up here. And that's what the green pictures is trying to identify. So during the testing, again, it's a variable frequency test. So obviously we do it at 60 hertz for leakage reactance, but you would hit the checkbox and it just varies the frequency. And as you increase the frequency, and if there's a strand to strand short, the frequency goes way. I mean, the the resistance goes really high as the frequency goes up. So you can kind of identify which phase it's on to. So it's really nice. Now the second test is like my favorite out of everything is called sweep frequency response analysis, SFRA. This is the test that looks at literally mechanical move, anything that moves in a transformer. This test set is great for that. And it's really easy to do as over time people have learned it's really not too challenging. I don't believe you need benchmark results for this because if you do it on a three phase, you'll see that you have 3 phases to analyze the results. But a transformer in general is a big RLC circuit made up of resistors, inductors, and capacitors. And as we do this measurement, so you're just gonna do a Bode plot, we're gonna do a whole frequency span. Everything will have a resonance point. So if these resonance points shifts up or down, or the curve starts shifting left or right, that means something physically changes. And SFRA can pick it up. So it's great for transportations. It's great for through faults or investigating any type of movements in a transformer. Some of the big ones that it can find is what's called radial deformation. So again, if that transformer that winding gets pushed out or pulled in, it can identify that pretty easier. If the winding gets pushed up or down, an overall movement of the winding, core lamination issues, core defects, um, core contact resistance, it can find it. I think that one is more challenging. It spots TTR like turns to turn short circuits pretty easily, and then open circuit windings as well. So when we perform the tests, we do again what's called an open circuit test, where we inject on the high side and we leave the low side open circuited. and we do a short circuit test. This is an example of the open circuit test. And each frequency range looks at different parts of the transformer. And the lower the frequency, the bigger it is inside the transformer. So you can obviously clearly see, even in this one, the open circuit, on that low side, you look at the core, and notice how there's one phase that's just like a V. That will be your middle phase of it that just has one resonance point. Your two outer phases, your A and your C, will have those two resonance points in that core frequency range. And your 60 hertz should align exactly with the same pattern as your exciting current test results. So your 60 hertz is two highs and a low, and we have two highs and a low here. And as it goes up in frequency, it will look at different parts of the transformer, your winding structure, leads, and then into connections as well. Your short circuit test, where we're going to short the low side, it takes the core out of the picture. So if I look at this, now there's none of those resonance that we just saw in that open circuit. We're literally just looking at the leakage channel, just exactly like the leakage reactance testing. So I can compare this to my leakage reactance and make sure, and this is done at really a very low voltage, maybe 10 volts to compare. It's a very low voltage. It's pretty amazing. Um, to look at this, and then into your winding structure, leads, and connections. So again, we would do a face-to-face comparison to do it. You really don't need, it's nice to have previous or benchmark, but if there's a big problem, you can it will stick out. Now, a newer test that is performed is called dielectric frequency response. And this is a more modern test that really tries to narrow down the big question of how wet is your transformer. Because one of the big problems, it's really challenging, is that a lot of the moisture in a transformer is in the paper. So everybody tries to take an oil sample and try to figure out and correlate how much water is in my oil to how much water is in my paper. And um, and I'll get into it a little bit, but this test really focuses directly on the paper itself, where the main all the water is for it. So there's no curves or graphs that you use or any of that to try to figure out and correlate um, the water content of your transformer. So overall, there's three main methods to try to figure out how wet your paper is, because the if you have a wet paper insulation, the life expectancy goes down tremendously. So, and it also depends on how hot you run your transformer. So the goal is to keep it dry, because you want to keep the life expectancy as long as possible, especially in this day and age of uh, right now. But with water content, is a direct measurement of how wet the paper is, and that's where DFR can do. ppm, that's where you would take an oil sample and you send it off to a lab, or you could use a portable one if you wanted, and take the oil and you figure out how many parts per million of water, and you use graphs, curves to figure out how much is related. But it's really, there's a lot of, it's not just, there's a lot that goes into it. And then relative saturation, which is, I think, better, but there's still a lot of gray area to figure out the relative saturation compared to how wet the paper is. So I'm focused on DFR, dielectric frequency response, and it's the best part about this is it's a super easy test. So it's really just a power factor test where you short the high side, short the low side, and it's great for what's called CHL and C1. So I just mentioned that. So if you want to look at the inside the transformer, how wet the paper is, we do it and focused on CHL because it's a UST test. And then a C1 if you really want to narrow down your bushing, the water content, and get a number. for it too. So it's a pretty simple, but it takes a little longer. This is an example I want to share with everybody of the different modes of power factor. So this is mode one, which is your standard 60 hertz power factor. These are three transformers. I meant four test results for CHL. We have red at 0.73, blue at 0.54, yellow 0.24, green at 0.22. So when you do it, if we do the second mode, which is extended power factor, now we start seeing a lot of differences between the slopes going through 60 hertz. So red is really downhill like this. Blue is getting kind of downhill. Yellow is starting to get there, and green is perfect. Green is like ideal to me when I look at these results. Now, say if I want to get a benchmark for my transformer when I first arrive, if I need to do a dry out of my transformer, so before it dries out, after it dries out, or if I'm doing a condition assessment and I need a health index, I want to know how wet the paper is. This is where DFR comes in, and this is an example of a complete DFR result. And what's great is the software will calculate your water content based on that curve. So the green one was 0.5, the yellow was 1.8, the blue was 2, and the green was 2.1. And these are just curves just to show you the impact of how much water can impact the curves, I mean the life expectancy of a transformer. So if the temperature at the transformer is around 90 degrees, the difference between, let's say, a half a percent, it would last around 50 years or so. And then that 2% would last around 7 years, that life expectancy. So it's really a big difference being able to measure that and then being able to try to dry it out too. And now that there's even online dry out systems that you can perform and still keep the transformer in service. So again, just a quick recap, you have your 60 hertz power factor. Um, One thing I didn't talk about test times is the test times of 60 hertz, about 5 to 10 minutes. You do it on CH, CHL, CL, C1, C2. You compare it to limits, pretty much compare to nameplate trending. Um, but 60 hertz power factor is not as sensitive to moisture. You have your extended, which is like 1 hertz to 500 hertz. It looks at a little bit more of the conductive losses that's happening. It's a little bit more moderate to paper moisture. It does take a little bit longer, about twice as long. It's the same connections as the standard 60 hertz, same test set. Interwinding, you do it on your interwinding in C1. You examine the curve and the slope, your trend, and similar assets, and it requires the um, a power factor test set to have it. So that's the one thing. And then the complete DFR, that's a separate test set. One thing is it could take a long time. It could take 30 minutes up to a couple hours, depending on how dry it is. The drier it is, the longer it takes. But what's really nice is it provides the moisture content and oil conductivity. It really is really nice for that, for a transformer. So I just want to end real quick on a final case study to share. This is a 1969 transformer, and basically it had a through fault. They took an oil sample, and it had 21 parts per million of acetylene. So a very big, high energy fault occurred. They knew it. So through fault, took the oil sample. What's important is they took a second oil sample and they received the same type of results. I think it was 19 parts per million. They did SFRA. So if you can try to figure out, remember the blue one here is actually, no, the green one here, that's the B phase. It has one. And then you got your two outer phases. I'm comparing it. Oh, this is the high voltage side. Everything looks good. The upper frequency, this is typically what I see in some test sets where the connections from the top of the transformer to the grounding, your grounding connections, if you're not good with consistent grounding, that's what can happen, but that's not a problem. That's outside the transformer. When I look at the low side, everything aligns except when you get to this frequency up here, you're getting these shifts going on, especially in this B phase of the trans. So, okay, so now we got something going on in the B phase for SFRA. Um, we looked at the short circuit tests, we zoomed in, and it wasn't, the leakage channel really wasn't too bad. So we were questioning. So they asked what other tests you could do. We recommended to perform leakage reactance. We kind of wanted to do kind of a gamut of mechanical tests as well. So we did leakage reactance, and the three-phase equivalent, the nameplate was 6.6. We measured 6.9. It is right at the limit. But when you did the per phase measurement, when we look at each phase, it was 9.62% different, which the B phase meaning big something physically changed on the B phase. FRSL was pretty dead on, no strand to strand shorts. So I was like, okay, but there's something physically wrong. And we happen to do winding resistance as well, and they all lined up at really 36. They all measured around 36. So what was nice is I haven't been involved in too many where they're gonna um, cut open the transformer in the field. So they invited me out there, cut it open in the field. Problem is, I get a phone call as I'm going, hey, Dave, we're delayed a little bit. When they cut it open, it caught on fire. So they didn't take out all the oil out of the transformer. And when they started to cut open the transformer, it caught on fire. So some of these pictures, it's very burnt, and that's not due to the fault. That's due to the fire that happened. And when I got up there on the ladder, it was crazy how things were so stuck to each other. I tried to take actually a broom and move. So it was like glue. I couldn't move anything. However, uh, you can start to see in this where, let me see here. You can kind of start to see right here, there'll be on this is the B phase, this A, B, C. And right here, there's start to be a little bit of a bulge going on. Um, I took pictures from both angles. So the B phase, it comes out over here and then returns back over here. And it was really nice. Fortunate it was towards the upper phase of it. Since the acetylene and the results, the leakage reactance results were so bad, they definitely, that's why they tore it down and wanted to do an investigation in the field. But yeah, but I just wanted to go through all the different tests and then open it up for any questions. I know we're a little bit short, but just again, thank you.